In 1882, a German mathematician named Felix Klein described an object that has no inside, not a metaphor, not a thought experiment, a mathematical surface where the distinction between interior and exterior simply does not exist. You cannot point to the inside of this object because there is no inside. You cannot point to the outside either because there is no outside. The two concepts which you have taken for granted every second of your life, which feel as fundamental to reality as up and down, are not properties of surfaces in general. They are properties of some surfaces. And the Klein bottle is not one of them. That was not controversial when Klein published it. Nobody debated it. It was proven, accepted, and filed away in the mathematical literature like it was a minor footnote. And for about a century, that is exactly how most people treated it. A curiosity, a party trick for mathematicians. You might have heard about topology as that branch of math where a coffee mug is the same as a donut. Maybe you saw a gif of one morphing into the other and thought, that is clever. And then you moved on with your life. I need you to not move on. Because what happened after Klein, what topology became in the 20th and 21st centuries, is something that should have fundamentally changed how every person on this planet understands reality. And it did not. Not because the results were uncertain, not because the evidence was weak, but because the implications are so uncomfortable that even the physicists who confirmed them have mostly refused to say out loud what they actually mean. Here is what topology proved. Shape is not real. And I do not mean that in some loose philosophical sense. I mean that the properties you think define the shape of an object, its angles, its distances, its curvature, how big it is, how round it is, how flat it is, those are the exact properties that topology strips away and discards as mathematically irrelevant. What survives, what topology considers the real properties of an object, are things like how many holes it has, whether it is orientable, whether it is connected. Abstract properties that you cannot see, cannot measure with a ruler, and in many cases cannot even visualize. And this is not just mathematics anymore. In 2016, the Nobel Prize in Physics went to 3 scientists who proved that the deepest properties of matter are governed by topology, not by chemistry or composition. In 2011, a team at Stanford used topology to find a subtype of breast cancer that every statistical method had missed, one with 100% survival rate. Your own DNA is topologically knotted, and your cells contain enzymes whose entire purpose is to unknot it. The hidden dimensions of string theory, if they exist, are topological shapes, and the overall shape of the universe itself, the largest physical question you can ask, is a topological question that Einstein's equations cannot answer. I have been down this rabbit hole for weeks now, and I keep arriving at the same place. If topology is right about what properties are real and what properties are not, then most of what you experience as solid, local, concrete reality is made of the properties topology throws away: distance, location, size, shape itself. These are the expendable ones. The things that survive are abstract invariants, mathematical objects that have no analog in the physical world your brain evolved to navigate. And the man who understood this better than anyone alive, who solved the deepest topological question ever posed in the history of mathematics, looked at the world that celebrated him, found it ethically intolerable, and disappeared. He has not been seen in public in nearly 20 years. He turned down $1 million. He turned down the highest honor mathematics can bestow, and he said something when he left that I think about constantly. He said, "It is not people who break ethical standards who are regarded as aliens. It is people like me who are isolated." His name is Grigori Perelman. We will come back to him, but not yet. The question I want you to sit with for the next 2 hours is this. If shape is not real, if the properties we thought defined objects are mathematically optional, then what is real about the physical world? Every section of what follows is going to try to answer that question, and every section is going to fail. Let me tell you how this started, because topology did not begin as a grand theory of reality. It began with a walk that could not be taken. In 1736, in the Prussian city of Königsberg, there was a river called the Pregel. The river split around 2 islands, and 7 bridges connected the islands to each other and to the 2 banks. The people of Königsberg had a Sunday puzzle. Could you walk through the city, cross every bridge exactly once, and return to where you started? Nobody could do it, but nobody could prove it was impossible either. The problem reached Leonhard Euler, arguably the greatest mathematician who ever lived, and his first reaction was dismissal. In a letter to the city's mayor, Karl Leonhard Gottlieb Eller, Euler wrote that the problem bears little relationship to mathematics. He thought it was beneath him. He was wrong, and the fact that he was wrong might be the most consequential mathematical mistake in history. Euler realized that the specific layout of the bridges did not matter, the distances did not matter, the angles did not matter. The only thing that mattered was connection. Which land masses were connected to which, and by how many bridges. He reduced the entire city to 4 dots and 7 lines. 4 land masses, 7 bridges. And he proved that an Eulerian path, a walk crossing each bridge exactly once, is only possible if at most 2 of the land masses have an odd number of bridges. Königsberg had 4 land masses with odd numbers. The walk was impossible. The paper he published in 1741 in the Commentarii Academiae Scientiarum Petropolitanae was the first theorem of what would become graph theory. But more than that, it was the first time a mathematician had solved a problem by throwing away everything we normally think of as geometric information: distances, angles, areas, coordinates, and keeping only the abstract structural relationships. That is topology, the study of what remains when you strip away everything that feels concrete. The field did not get its name until 1847, when Johann Benedict Listing, a physicist and mathematician at Göttingen, who had studied under Gauss, published a book called Vorstudien zur Topologie. He had actually coined the word 11 years earlier in a private letter to a former teacher in 1836, combining the Greek topos, meaning place, with logos, meaning study. But what you need to understand is this. The English-speaking world did not have the word topology until Listing's obituary appeared in Nature in 1883. For decades, the field existed in German and French without a name in English. It was called analysis situs, Latin for analysis of position, a term Euler himself had suggested. It took until the late 1920s for Solomon Lefschetz to popularize the English word, an entire branch of mathematics that would eventually govern quantum physics, cancer research, and cosmology, spent the better part of a century without a name people could agree on. And then, in 1895, Henri Poincaré published a 121-page paper called Analysis Situs in the Journal de l'École Polytechnique, followed by 5 supplements over the next 9 years, and he broke the field wide open. He invented the fundamental group. He invented homology. He proved the Poincaré duality theorem. And in his fifth supplement, published in 1904, he asked a question that would haunt mathematics for a century. A question about the shape of three-dimensional space. A question that a reclusive Russian would answer 98 years later and then refuse to accept credit for. But I am getting ahead of myself. Before we can understand what Perelman solved, you need to understand what topology does to the concept of shape. Because the coffee mug and the donut thing is not a cute analogy. It is a statement about reality, and the full version of that statement is far more disturbing than the gifts suggest. A topologist does not care about shape. A topologist cares about properties that survive continuous deformation, which means stretching, bending, squishing, and warping, but never tearing and never gluing. If you can transform one object into another without ripping it apart or fusing pieces together, those two objects are topologically identical. The technical term is homeomorphic, a word Poincaré coined from the Greek for same form. And a coffee mug is homeomorphic to a donut because both have exactly one hole. The handle of the mug maps to the hole of the donut, and you can smoothly deform one into the other without tearing. That means, in the language of topology, a coffee mug and a donut have the same shape. The fact that one is concave and the other is convex does not matter. The fact that one has a flat bottom and the other is round does not matter. The fact that one is 3 inches tall and the other is 1 inch tall does not matter. Distance, angle, curvature, volume, all of these are geometric properties, and topology discards every single one of them. What topology keeps are called topological invariants, the number of holes which mathematicians call the genus, whether the surface is orientable, meaning whether you can consistently define a clockwise direction everywhere on it, whether it is connected, meaning whether it is one piece, the number of boundary components, the dimension, that is it. Those are the real properties. Everything else is noise. And here is where I need to correct something that you have probably seen in every pop science explanation of topology, because the standard version undersells what is actually happening. The coffee mug and donut equivalence is not about physically stretching objects. Nobody is claiming you can take a ceramic mug and physically reshape it into a pastry. The claim is deeper than that. The claim is that the properties which distinguish a mug from a donut, its concavity, its flatness, its angularity, are not topological invariants. They are geometric properties. And topology says geometric properties are not the real ones. Topology says if you want to understand what an object fundamentally is, you ignore geometry entirely. You ask only about the invariants. And by those standards, a coffee mug and a donut are the same object. Think about what that means for a second. You live in a world where you navigate by geometry. You recognize objects by their shapes, their sizes, their angles. Your brain evolved to process geometric information because geometry is useful for survival. But topology says geometry is the surface layer. Underneath it, the real properties are abstract integers and equivalence classes. You have been looking at the decoration and ignoring the structure. In 2003, a team of physicists published a paper in Nature proposing that the universe itself might be one of these abstract, topological shapes, a finite space that wraps around itself in a way that cannot be visualized. constructed from a regular dodecahedron with its opposite faces identified after a 36-degree twist. And Einstein's equations, the most precisely tested equations in the history of physics, offer no way to determine whether they are right. General relativity tells you about local curvature. It says nothing about global topology. The shape of the universe is a question physics cannot answer. We will get there. But first, you need to see what happens when you take topology's claim seriously. Because if inside and outside are just geometric properties, then there should be surfaces that do not have them. And there are. In 1858, two mathematicians independently discovered the same impossible surface. August Ferdinand Mobius was 68 years old, a professor of astronomy at Leipzig who had spent decades directing the university's observatory. He was not a topologist. The field barely existed. He was working on the classification of surfaces, trying to understand orientability, which is the question of whether you can consistently define a direction of rotation at every point on a surface. And he found a surface where you cannot. Take a strip of paper, give it a half twist, glue the ends together. You have made a Mobius strip. And it is one of those objects that seems simple until you actually think about what it means. Put an ant on the outside of the strip. Let it walk straight ahead. The ant will traverse what appears to be the inside of the strip without ever crossing an edge, and it will arrive back where it started. The strip has one side, not two sides that are connected. One side, period. The concept of this side versus that side does not apply. There is only one side to be on. Cut the strip down its center line. A normal loop would split into two separate loops. The Mobius strip does not. It becomes one larger loop with two full twists. It refuses to separate. Cut that larger loop down its center line, and you get two interlocked loops. The object resists every attempt to reduce it to something familiar. Johann Benedict Listing discovered the same surface independently, also in 1858, and actually published his findings first in 1861. Mobius did not publish until 1865. There is a quiet historical injustice here. Listing coined the word topology. He co-discovered the Mobius strip months before Mobius, and history gave the other man credit for both. I personally think Listing is one of the most underrated figures in the history of mathematics, and the fact that the strip does not bear his name is the kind of small, compounding injustice that defines how mathematical credit works. There is also speculation that Gauss, who supervised both Listing and Mobius at different points, may have planted the seed for the discovery in conversations with each of them. We will never know. Gauss was famously secretive about his ideas, publishing only results he considered polished enough for posterity. His notebooks, discovered after his death, contained decades of unpublished work that anticipated entire fields. But the Mobius strip is just the appetizer, because if one-sidedness is possible, if the distinction between inside and outside is not a necessary property of surfaces, then what else is optional? Felix Klein answered that question in 1882, and the answer is worse than you think. Klein was born in Dusseldorf in 1849 and had one of the most brilliant early careers in mathematical history. At 23, he formulated the Erlangen program, a manifesto that reorganized all of geometry based on group theory and symmetry, an idea so far ahead of its time that it took decades for the rest of mathematics to catch up. But in that same year, 1882, Klein suffered a severe depressive episode that essentially ended his research career. He was 33 He would live another 43 years, becoming one of the greatest mathematical educators in history. But he never produced original research at the same level again. And the object he described that year in a book on Riemann surfaces would turn out to be one of the most important surfaces in mathematics. The Klein bottle is a closed surface that has no inside and no outside. Let me be precise about what that means. The Mobius strip has no consistent orientation, but it has an edge, a boundary. The Klein bottle has no boundary. It is a closed surface, and it is non-orientable. There is no way to consistently define interior versus exterior. The concepts do not apply. An ant on a Klein bottle can walk from any point to any other point without ever crossing a boundary, because there is no boundary. And it will find itself on both sides of the surface, because there is only one side. Here is the part that gets uncomfortable. A Klein bottle cannot exist in three-dimensional space without passing through itself. If you try to build one, the surface has to intersect itself, which breaks the rules. The Klein bottle requires four-dimensional space to exist without self-intersection. This is not a limitation of our engineering. It is not that we lack the technology to build a true Klein bottle. It is that three dimensions are not sufficient to contain it. The object is mathematically real and physically unconstructible in the space we inhabit. You can build a Klein bottle by taking two Mobius strips and gluing them along their edges. Or you can think of it like this. Take a square, glue the top edge to the bottom edge, making a tube. Now glue the left edge to the right edge, but with a flip so that the direction is reversed. In three dimensions, you cannot do this without the tube passing through itself. In four dimensions, it works perfectly. The Euler characteristic of a Klein bottle is 0, same as a torus, but a torus is orientable. A Klein bottle is not. That single difference, orientability, is the property that determines whether a closed surface has an inside. And here is what the classification of surfaces theorem says. The result that Mobius began working toward in 1861, and that Brahana finally proved rigorously in 1921. Every compact, connected closed surface in existence is topologically equivalent to exactly one member of a list. Orientable surfaces are spheres with handles. 0 handles gives you a sphere. 1 handle gives you a torus. 2 handles gives you a double torus, and so on. Non-orientable surfaces are spheres with crosscaps. 1 crosscap gives you the real projective plane. 2 crosscaps give you a Klein bottle. That is the entire catalogue of closed surfaces. Every one, the infinite variety of shapes you see in the world. Every curved, angled, bumpy, smooth, irregular surface you have ever touched collapses into a list indexed by 2 properties. The Euler characteristic, which is an integer, and whether the surface is orientable, which is a yes or no. That is all there is. Shape is not a continuum. It is not a spectrum. It is a discrete catalogue, and the catalogue is short. I spent an embarrassingly long time staring at this result when I first encountered it, because the implications kept unfolding. Think about what it means for the concept of identity. You look at a crumpled piece of paper and a smooth sphere, and you see 2 completely different objects. Topology says they are the same. You look at a pretzel and a mug with 2 handles, and you see nothing in common. Topology says they are the same. The entire visible world of shape, every object you have ever recognized, every form your visual cortex has ever processed, is a geometric overlay on a topological skeleton that is shockingly sparse. The skeleton has integers. The overlay has beauty. And topology says the skeleton is what is real. But maybe this is just mathematics. Maybe the physical world operates differently. Maybe atoms and molecules and matter have properties that are genuinely, irrevocably their own. Properties that cannot be deformed away. That would be comforting. That would mean topology is a mathematical framework that describes abstract surfaces but does not reach into the physical world. That hope lasted until the 20th century, when physicists discovered that the deepest properties of matter are not chemical. They are not structural. They are topological. And the discovery happened, as so many of the best discoveries do, entirely by accident. In 1867, one of the most respected physicists in the British Empire had a beautiful idea. Lord Kelvin, born William Thomson, proposed that atoms were knots. Specifically, he proposed that atoms were knotted vortices in the luminiferous ether, the invisible medium that was supposed to permeate all of space. Different types of knots would correspond to different chemical elements. A simple unknotted ring would be hydrogen. A trefoil knot, the simplest non-trivial knot with 3 crossings, would be another element. A figure 8 knot with 4 crossings would be another. The periodic table of elements would be a table of knots. The idea was inspired by 2 things. First, Hermann von Helmholtz had proven in 1858 that vortex filaments in a perfect fluid are permanent. They cannot be created or destroyed, and their topology is conserved. A knotted vortex stays knotted forever. Second, and this is the part that makes the story come alive, Peter Guthrie Tait had built an apparatus that generated smoke rings. In January of 1867, Tait demonstrated these smoke rings for Kelvin, and the behavior was stunning. The rings bounced off each other elastically. They vibrated at specific frequencies. They could not be cut apart. They behaved, in short, exactly how you would want atoms to behave. Kelvin saw the demonstration and immediately began developing his vortex atom theory, publishing it that same year in the Proceedings of the Royal Society of Edinburgh. The theory was popular for over 20 years. Roughly 60 papers by about 25 scientists explored the idea. It explained why atoms were permanent, why they came in discrete types, and why they had specific spectral signatures. It was elegant, it was compelling, and it was completely wrong. The Michelson-Morley experiment of 1887 failed to detect the aether. J.J. Thomson's discovery of the electron in the 1890s revealed subatomic structure that vortex atoms could not account for. 3-dimensional vortex structures turned out to be dynamically unstable. By around 1890, Kelvin himself had abandoned the theory. But here is the part that should genuinely unsettle you. The theory was wrong about physics, but it accidentally created an entire branch of mathematics that more than a century later turned out to govern physics in ways Kelvin never imagined, because Tait did not stop. Even after the vortex atom theory collapsed, Peter Guthrie Tait kept cataloguing knots. He had been doing it since 1876, motivated initially by Kelvin's theory, but the work took on a life of its own. Tait was senior wrangler at Cambridge in 1852, a close friend of James Clerk Maxwell, and professor of natural philosophy at Edinburgh from 1860, and he approached knot enumeration with the obsessive rigor of a man who believed he was building the periodic table of nature. By 1877, he had classified all knots with up to 7 crossings. Working with Reverend Thomas Kirkman, who generated the knot projections, and Charles Newton Little, who checked for equivalences, Tate published complete tables of knots with up to 10 crossings by 1885. And those tables were almost entirely correct for over a century. The single error, 2 10-crossing knots listed as distinct that are actually the same knot, was not discovered until 1974 by Kenneth Perko. It is now called the Perko pair. 114 years of a wrong entry in a mathematical table. That is either a testament to the difficulty of the problem or to the quality of Tate's work. Probably both. Tate also formulated 3 conjectures about alternating knots in the 1870s and 80s. 2 of them were not proven until 1987 by Louis Kaufmann, Kunio Murasugi, and Morwen Thistlethwaite, working independently. The third was proven in 1991 by Thistlethwaite and William Manasco. Resolution time for Tate's conjectures, 104 to 114 years. This man posed questions in the 1880s that the best mathematicians on Earth could not answer until the late 20th century. And he was doing it as a side project while teaching physics. And there is an even deeper problem lurking underneath the enumeration, the unknotting problem. Given a tangled diagram of a curve in space, how do you determine whether it is genuinely knotted or just a complicated picture of the unknot? A circle that is being drawn with gratuitous crossings but is not actually knotted? Wolfgang Haken proved in 1961 that the problem is at least decidable, meaning an algorithm exists. But the computational complexity is staggering. In 1999, Haas, Lagarius, and Pippinger proved the unknotting problem is in the class NP, meaning a solution can be verified quickly. In 2016, Mark Lackenby proved it is also in co-NP, but whether it can be solved in polynomial time, whether there is a fast algorithm, remains one of the major open problems in computational topology. In 2021, Lackenby announced a quasi-polynomial time algorithm, but as of late, 2025, it has not appeared in peer-reviewed literature. The question of whether you can efficiently determine if a knot is really a knot is unresolved. And I find this deeply strange. We live in a universe where knots are everywhere, in proteins, in DNA, in quantum field theories, in the fabric of space-time itself, and we do not have a fast way to tell if a knot is actually there. The universe ties knots faster than we can recognize them. But the real revolution came in 1984, and it came from someone who was not even looking for it. Vaughan Jones was a New Zealander, born in Gisborne on December 31st, 1952, and he was working at the University of Geneva on something called subfactors of type 2-1 von Neumann algebras. This is deep operator algebra, about as far from knot theory as you can get within pure mathematics. But Jones noticed that formulas in his nested algebras, specifically the Temperley-Lieb algebra, looked eerily similar to the algebraic relations governing braids, groups of strands woven over and under each other. He contacted Joan Berman, a topologist at Columbia University, and asked whether this resemblance meant anything. Berman explained that a braid can be closed up to form a knot, a standard construction in topology. And when Jones fed knots through his algebraic machinery, out came a polynomial, a mathematical expression associated with each knot that was invariant under deformation, a new knot invariant. the first one discovered since James Waddell Alexander's polynomial in 1928. A gap of 56 years broken by someone who was not a topologist, was not studying knots, and stumbled onto the connection by accident. I want to sit with that for a moment because I think it is the most underrated part of this entire story. For over half a century, topologists had been trying to find new knot invariants and failing. The problem was considered essentially stuck. And then a man from New Zealand working on operator algebras just walked in through the side door and solved it. Because his abstract algebraic structures happened to encode the same information as knotted loops in three-dimensional space. The universe did not keep knot theory and operator algebra in separate boxes. They were always the same subject. Nobody knew. Jones presented his polynomial on May 22, 1984, at Columbia University. He published it in the Bulletin of the American Mathematical Society in 1985. The Jones polynomial could do something the Alexander polynomial never could. It could distinguish mirror images of knots. A left-handed trefoil and a right-handed trefoil, which the Alexander polynomial treats as identical, have different Jones polynomials. Chirality, handedness, was visible to the new invariant. Jones won the Fields Medal in 1990 at the International Congress of Mathematicians in Kyoto. He wore an all-blacks rugby jersey to the ceremony. I love that detail. The most prestigious award in mathematics, the ceremony steeped in protocol and formality, and the man who earned it showed up repping his national rugby team. That is not something a template produces. But the Jones polynomial was just the beginning. Within a year of his announcement, 5 independent groups had found a generalization. The result was the HOMFFI polynomial, named for its discoverers, Hoste, Ognianu, Millet, Freyd, Licorice, and Jeter. It was later extended to HOMFLIPT to credit 2 additional discoverers, Joseph Pszczycki and Paweł Traczyk. Their publication was delayed until 1987 because of martial law in Poland. Think about that. 2 mathematicians had independently proven a major result in knot theory and could not publish it because their country was under military rule. Mathematical truth held hostage by political oppression. When their paper finally appeared, the acronym was updated. A small act of justice encoded in 6 letters. And then Edward Witten did something that blurred the line between mathematics and physics permanently. Witten is the only physicist ever to win the Fields Medal. He received it in 1990, the same year as Jones. And for good reason. Witten showed that the Jones polynomial could be interpreted as a path integral in Chern-Simons gauge theory, a topological quantum field theory in 3 dimensions. Let me translate that. The mathematical fingerprint of a knotted loop in space. The Jones polynomial is a quantity that a quantum field theory can compute. Knot invariants are not just abstract mathematical tools. They are physical quantities. They arise from the same formalism that governs how particles interact. Witten was born in Baltimore in 1951. He got his bachelor's degree in history from Brandeis in 1971, briefly worked on George McGovern's presidential campaign, then pivoted to physics, and earned a PhD from Princeton under David Gross in 1976. A historian turned political campaigner turned physicist who won the highest prize in mathematics. His 1988 paper, Founding Topological Quantum Field Theory, has been cited thousands of times. The International Congress citation for his Fields Medal noted that his ideas, although mostly not in the form of completed proofs, had triggered major mathematical developments by the force of their vision. They gave a physicist the top math prize and admitted that his contributions were not fully proven. That is how far ahead of the field he was. The work did not need to be finished to be recognized as the foundation of an entire discipline. And Witten's result points to something that I think physicists have not publicly reckoned with. If not invariants are physical quantities, if the abstract mathematical properties of tangled loops arise naturally from quantum field theory, then topology is not describing reality from the outside. It is not an approximation or a model. It appears to be the language that reality is written in. The boundary between abstract mathematics and physical law is not where anyone thought it was. But here is where it gets worse. Because all of this, the knot theory, the Jones polynomial, the connection to quantum field theory, is preparation for what happened in 2016. The year the Nobel Committee told the world that the deepest properties of matter are topological. In the early 1970s, two British physicists at the University of Birmingham were working on a problem that most of their colleagues considered solved. The problem was whether ordered phases of matter could exist in two dimensions. The conventional wisdom, based on the Mermin-Wagner theorem, said no. You cannot have long-range order in a two-dimensional system at finite temperature. Thermal fluctuations destroy it. The question was considered closed. Michael Kosterlitz and David Dowless disagreed, and what they found overturned the conventional picture entirely. In two papers published in 1972 and 1973 in the Journal of Physics C, they showed that in two-dimensional systems described by the XY model, something extraordinary happens. At low temperatures, vortex-antivortex pairs bind tightly together. Above a critical temperature, they unbind. And this unbinding transition, now called the Berezinski-Kosterlitz-Dowless transition or BKT transition, is a phase transition unlike any that had been seen before. It has no conventional order parameter. There is no symmetry that breaks. It is a phase transition of infinite order, driven entirely by the topology of vortex configurations. A Soviet physicist named Vadim Berezinski had independently reached similar conclusions in 1971, but his work was largely unknown in the West. A decade later, Duncan Haldane, working at the Université de Paris Sud, published two papers in 1983 that predicted something even stranger. He showed that antiferromagnetic spin chains, simple one-dimensional chains of quantum magnets, behave completely differently depending on whether their spin is an integer or a half-integer. Integer spin chains have an energy gap, now called the Haldane gap, of approximately 0.41 times the coupling constant J for spin 1 chains. Half-integer spin chains are gapless. The only difference is an integer versus a half-integer, a topological distinction, and it determines the fundamental physical behavior of the system. But the result that should have made front-page news, the one that connects topology to something you can measure in a lab to 9 decimal places of accuracy, came from a paper published in 1982. The authors were Dowless, Komoto, Nightingale, and Den Nys. The paper appeared in Physical Review Letters, volume 49, page 405. It is known as the TKNN paper, and it explained why the quantum Hall effect is quantized. Klaus von Klitzing had discovered the quantum Hall effect in 1980, winning the Nobel Prize in 1985. When you put a 2D electron gas in a strong magnetic field, the Hall conductance, which measures how current flows perpendicular to an applied voltage, does not vary smoothly. It jumps in exact integer steps. Exact. not approximately integer, not very close to integer. Integer, measured to parts per billion. The TKNN paper explained why. The Hall conductance equals E squared over h, the fundamental charge squared divided by Planck's constant, multiplied by an integer called the first Chern number. The Chern number is a topological invariant. It is computed as the integral of Berry curvature over the magnetic Brillouin zone. And because it is a topological invariant, because it is an integer, and because integers cannot change continuously, the quantization is exact and robust. It does not depend on the purity of the sample. It does not depend on the precise shape of the material. It does not depend on temperature variations or defects or impurities. The Hall conductance is quantized because the mathematics of topology says integers cannot be slightly different from integers. This is the point where topology stops being abstract and becomes physical law. An integer in a mathematical space you cannot see, cannot touch, and cannot directly measure determines whether electrons flow through a material. And not just approximately, exactly. The quantum Hall effect is now used as the international standard for electrical resistance because it is more precise than any physical artifact. After the TKNN paper, an entire field opened up. Topological insulators, materials that conduct electricity on their surface but insulate in their bulk. The surface conducting states are protected by topology. You cannot destroy them without closing the bulk energy gap, which is the topological equivalent of removing a hole from a donut. You would have to destroy the donut. Charles Kane and Eugene Mellet at the University of Pennsylvania predicted the theoretical framework in 2005, introducing the Z2 topological invariant. In 2006, Bernavig, Hughes, and Zhang predicted the first realistic two-dimensional topological insulator in mercury telluride quantum wells. And in 2007, Lorenz Molenkamp's group at the University of Würzburg confirmed it experimentally, observing quantized conductance of 2e squared over h, exactly as predicted. The first three-dimensional topological insulator, bismuth antimony, was observed by Zahid Hassan's group at Princeton in 2008. Bismuth telluride and bismuth selenide in 2009 were confirmed that same year with bulk energy gaps of around 0.3 electron volts, large enough for room temperature effects. And the key line, the one that I think should disturb you, is this. A topological insulator and a trivial insulator can have nearly identical crystal structures and chemical compositions. The atoms can be the same. The bonds can be the same. The arrangement can look the same under an electron microscope, but one conducts on its surface and the other does not, because they have different Chern numbers, different topological invariants in momentum space. The difference between them is an integer that lives in an abstract mathematical space, not in the physical world you can see and touch. The properties of matter are not determined by what matter is made of. They are determined by the topology of abstract mathematical spaces that describe how quantum wave functions behave. That is not a metaphor. That is what the 2016 Nobel Prize was awarded for. And here is the scandal. These results were obtained in the 1970s and 80s. The BKT transition was published in 1972. The TKNN paper was published in 1982. Haldane's Conjecture was published in 1983. It took 30 to 44 years for the Nobel Committee to recognize work that fundamentally changed what we know about matter. For decades, topological phases were considered a niche curiosity. Haldane himself said upon receiving the Nobel, "We did not think it would ever find practical realization. The physics community had the answer for 40 years. They just did not think it mattered." Meanwhile, Microsoft has bet its entire quantum computing future on topology. Their station QLab, led by Chetan Nayak at UC Santa Barbara, has pursued topological qubits using Majorana zero modes, exotic quasiparticles. The idea is that information stored in the non-local topology of these quasiparticles would be inherently protected from the decoherence that plagues conventional quantum computers. In 2018, a Nature paper from the team at Delft, led by Leo Koeenhoven, claimed to have observed quantized Majorana conductance. In 2021, that paper was retracted after Sergei Frolov and Vincent Morik found data inconsistencies. The researchers had selected data in a biased way. In February 2025, Microsoft announced Majorana 1, an 8-qubit topological quantum processor, accompanied by a new Nature paper. Frolov called the project essentially fraudulent. The trillion-dollar company and the skeptics are still arguing. The science is not settled. The abdication of authority is happening in real time, in one of the most expensive research programs in history, and the public barely knows about it. But even if you set aside the controversy, even if every Microsoft claim turns out to be correct, the implications are the same. The future of computing, the technology that may define the next century, rests on a mathematical property of abstract spaces. Topology is not just governing matter, it is being engineered. There is a woman who belongs in this part of the story, and the fact that she is not more famous is one of the quieter injustices in the history of science. Emmy Noether was born in Erlangen in 1882, the same year Klein described his bottle. She entered the University of Erlangen at a time when women could only audit classes, one of 2 women among 986 students. She completed her doctorate summa cum laude in 1907 and then worked without pay or title for 7 years. When David Hilbert and Felix Klein tried to bring her to Göttingen in 1915, the faculty objected. "What will our soldiers think?" they asked, "when they are required to learn at the feet of a woman?" Hilbert's response has become legendary. "I do not see that the sex of the candidate is an argument against her admission. After all, we are a university, not a bathhouse." She was denied the position anyway. For 4 years, she lectured under Hilbert's name. On July 26, 1918, Klein presented her theorem. She was barred from presenting it herself. Noether's theorem states that every differentiable symmetry of a physical system corresponds to a conservation law. Conservation of energy comes from time symmetry. Conservation of momentum comes from spatial symmetry. Conservation of angular momentum comes from rotational symmetry. It has been called one of the most important theorems ever proved in guiding the development of modern physics. She did not receive a salary until 1923. She was 41 years old. Her colleague Herman Weyl wrote, "I was ashamed to occupy such a preferred position beside her whom I knew to be my superior as a mathematician in many respects." In 1933, she was among the first professors fired under Nazi anti-Jewish laws. She fled to Bryn Mawr College in Pennsylvania. She died on April 14, 1935, at age 53, from complications after surgery. Einstein's tribute appeared in the New York Times on May 4, 1935. He wrote that in the judgment of the most competent living mathematicians, she was the most significant, creative mathematical genius produced since the higher education of women began. What connects Noether to topology specifically is this. She was the one who suggested that topological properties should be studied through algebraic structures, through groups and rings and modules, rather than through intuitive geometry. Her algebraic approach transformed topology from a field of rubber sheet visualizations into a rigorous algebraic discipline. The homology groups that Poincaré had introduced, Noether insisted on treating as genuine algebraic objects with their own internal structure. She gave topology its modern language, and the field repaid her by not giving her a salary for the first 16 years of her career. So the properties of matter are topological. The deepest symmetries of physics are topological. The mathematical framework that makes all of this precise was shaped by a woman who was denied recognition at every turn. But at least biology, surely biology is different. The physical machinery of life operates in three-dimensional space. Proteins fold into specific shapes. DNA has a structure, a famous one, the double helix that Watson and Crick described in 1953. This is geometry, tangible, spatial, physical geometry. The shape of molecules is what makes biology work. Except your DNA is knotted, and the enzymes that unknot it are doing topology. And they have been doing it for billions of years before any human thought to write down the rules. DNA does not just sit neatly in your cells like thread on a spool. It tangles, it knots, it overwrites itself in loops and supercoils that would make a sailor wince. A single human cell contains roughly 2 meters of DNA packed into a nucleus that is about 6 micrometers across. That is the equivalent of stuffing 40 kilometers of thread into a tennis ball. And when that thread needs to be read, copied, or repaired, it has to be locally untangled, processed, and repacked without breaking. If the topology goes wrong, if a knot forms in the wrong place or a link between 2 chromosome copies is not removed, the cell either dies or becomes cancerous. Topology is not an abstraction in biology. It is a matter of life and death. The molecular machines that manage this are called topoisomerases, and they are, without exaggeration, the most sophisticated topological engines in the known universe. They were not designed by mathematicians. They were evolved by natural selection over billions of years. And they perform operations that a knot theorist would recognize immediately. There are 2 types. Type 1, topoisomerases, first discovered by James C. Wang in 1971, cut a single strand of DNA, allow the other strand to pass through the gap, and reseal the break. This changes the linking number by 1. It can relieve supercoiling, but it cannot resolve knots. Type 2 topoisomerases, first discovered by Martin Gellert in 1976, do something far more dramatic. They cut both strands of the double helix simultaneously, pass an intact double helix through the gap, and reseal both cuts. This changes the linking number by 2, and this is the only molecular mechanism in biology that can unknot DNA. In 1997, Rybankov et al. Published a paper in Science, volume 277, page 690, that showed something astonishing. Type 2 topoisomerases do not just unknot DNA. They reduce the knotting level to 80 times below what thermodynamics would predict. 80 times. If you just left DNA to equilibrate thermally, it would be far more tangled than what you actually find in cells. These enzymes actively burn ATP, spending energy to simplify topology. They are a molecular Maxwell's demon. They push the system far from equilibrium specifically to maintain topological simplicity. Think about that. Your cells contain molecular machines that consume energy for the sole purpose of performing topology on the molecule that encodes your existence. They cut, they pass, they reseal, over and over, every time your DNA is replicated, transcribed, or repaired. The entire operation is topological. The enzyme does not care about the sequence of base pairs passing through its active site. It does not read the genetic code. It reads the topology. It detects whether the DNA is knotted or linked, and it resolves the entanglement. And we exploit this. Anti-cancer drugs like etoposide and doxorubicin work by trapping type 2 topoisomerases on DNA, converting the cell's own topological machinery into a poison. The enzyme cuts both strands, but the drug prevents it from resealing the break. The result is a double-strand break, the most lethal form of DNA damage. The cell's own topology engine kills it. Fluoroquinolone antibiotics, like ciprofloxacin, do the same thing to bacterial topoisomerases. Every time you take ciprofloxacin for an infection, you are waging topological warfare on bacteria. The pharmaceutical industry is in part a topological engineering enterprise, and I have never heard anyone frame it that way. The pioneering work connecting knot theory to DNA was done by DeWitt Sumners and colleagues in the late 1980s and early 1990s. The tangle calculus developed by Ernst and Sumners in 1990, published in the Mathematical Proceedings of the Cambridge Philosophical Society, allowed researchers to deduce the mechanism of an enzyme by analyzing the knot types it produces. You give the enzyme a circular piece of DNA. You let it act. You look at what knot type comes out. And from the knot type, you can work backwards to figure out what the enzyme did. The DNA is the answer sheet. The knot theory is the decoder. Wasserman, Dungan, and Cozzarelli had already shown in 1985 in a paper in Science that a specific predicted DNA knot type produced by the TN3 resolvase enzyme matched the theoretical prediction. Biology was generating knots that mathematicians had catalogued on paper. The collaboration between molecular biology and knot theory, two fields that seem to have nothing in common, has been one of the most productive interdisciplinary marriages in modern science. Colin Adams, the Thomas T. Reed Professor of Mathematics at Williams College, wrote the knot book in 1994, published by W.H. Freeman, which made this entire connection accessible to non-specialists and remains the best popular introduction to the subject. He has supervised over 130 undergraduate research students and made knot theory one of the most approachable branches of modern mathematics. But here is where the story takes a turn I was not expecting when I started this research. Because topology does not just govern biological molecules, it governs the shape of biological data. And the person who showed this is a Stanford mathematician named Gunnar Carlsson. And the result should have changed medicine. Carlsson was born in Stockholm on August 22nd, 1952. He spent most of his career in pure algebraic topology, the kind of abstract mathematics that has no obvious connection to the real world. But in the 2000s, he became obsessed with an idea. Data has shape, not metaphorically, literally. A set of data points in a high-dimensional space forms a shape, a topological space with its own connected components, loops and voids. And that shape carries information that statistical methods cannot see. The technical framework is called persistent homology. Imagine you have a cloud of data points. You start drawing bubbles around each point. As the bubbles grow, some of them overlap and merge. Connected components disappear as clusters fuse. Loops appear as bubbles surround empty regions. Voids form as bubbles enclose empty cavities. And each of these topological features, each connected component, each loop, each void has a lifetime. It is born when it first appears, and it dies when it merges or fills in. Features that persist across a wide range of scales are real structure. Features that appear and vanish quickly are noise. The result is a persistence diagram, a visual map of the topology of data across all scales simultaneously. The stability theorem, proved by Cohen-Steiner, Edelsbrunner, and Hare in 2007, guarantees that small changes in data produce small changes in the persistence diagram. This is not true of clustering methods like k-means, which can give wildly different results depending on arbitrary choices of parameters. Persistent homology is stable, robust. It detects genuine topological features that do not depend on how you choose to look at the data. Carlson's landmark paper, Topology and Data, published in the Bulletin of the American Mathematical Society in 2009, Volume 46, Number 2, pages 255 through 308, laid out the manifesto. It has been cited over 2,400 times, and in 2008, he co-founded IASTI, the first company to commercialize topological data analysis. But the result that I keep coming back to, the one that genuinely altered how I think about what mathematics can do, was published in 2011. The paper is by Monica Nicolaou, Arnold Levine, and Gunnar Carlson, published in the Proceedings of the National Academy of Sciences on April 11, 2011. The title is Topology-Based Data Analysis Identifies a Subgroup of Breast Cancers with a Unique Mutational Profile and Excellent Survival. Levine, by the way, is the co-discoverer of the p53 tumor suppressor gene and was at the Institute for Advanced Study in Princeton when this work was done. Here is what they did. They took gene expression data from breast cancer patients and applied a topological method called MAPPER, combined with what they called progression analysis of disease, standard statistical methods, hierarchical clustering, and k-means had been applied to this same data before. Those methods found the known subtypes, luminal A, luminal B, basal, HER2 enriched, the usual categories. Topology found something else, a subgroup of estrogen receptor positive breast cancers characterized by high expression of CMYB and low expression of innate inflammatory genes. This subgroup had 100% survival and 0 metastasis. Let me say that again. 100% survival, 0 metastasis. This subtype was invisible to standard clustering because it did not form a discrete cluster. It occupied a continuous branching structure in the high-dimensional data space, a shape that only topological methods could detect. Statistics looked at the data and saw noise. Topology looked at the same data and saw a group of patients who were going to survive. This was published in PNAS in 2011. It has been cited over 570 times, and it did not make headlines. It did not change clinical practice. It did not transform how oncologists think about breast cancer subtypes. It sits in the literature, cited mostly by other mathematicians and data scientists, while clinicians continue to rely on methods that cannot see the shapes hiding in their data. I have been thinking about this for days, and I still do not fully understand why it did not land harder. A mathematical method found a cancer subtype with perfect survival that no other method could detect. That should have been front-page news. It was not. And I think the reason is that topology is too alien for most biomedical researchers to integrate into their workflows. The math is hard. The intuition is unfamiliar. The tools require a completely different way of thinking about data. So the result sits there, confirmed, published, ignored. And it is not the only application. Gaidier and Katz published in 2018 in Physica A, showing that persistence landscape norms, a topological summary statistic, exhibited strong growth 250 trading days before both the 2000 dot-com crash and the 2008 Lehman Brothers bankruptcy. The shape of financial data predicted catastrophe 8 months in advance. Researchers at the Blue Brain Project, led by Raymond et al. In 2017, found up to 11-dimensional topological structures in neural networks, structures invisible to any non-topological method. Hiraoka et al. At Tohoku University, publishing in PNAS in 2016, used persistent homology to reveal hidden hierarchical structures in amorphous solids that conventional analysis could not detect. And then there is the result from Carlson et al. In 2008, published in the International Journal of Computer Vision. They analyzed the space of natural image patches, the tiny fragments of visual information that your brain processes every moment. And they found that this space, the mathematical landscape of everything your eyes see, concentrates on a shape that is topologically equivalent to a Klein bottle. Let that sit for a moment. The object that has no inside or outside. The surface that cannot exist in 3 dimensions without self-intersection. The mathematical impossibility that Felix Klein described in 1882 is embedded in the structure of human vision. The way your brain processes visual information has the topology of an object that should not exist in your physical world. And nobody told you. This is the point in the script where I should introduce Maryam Mirzakhani. And I want to do it properly because her story is one of the most remarkable in the history of mathematics and also one of the most painful. She was born on May 12, 1977, in Tehran. She won a gold medal at the International Mathematical Olympiad in 1994, scoring 41 out of 42. The next year, she won again, this time with a perfect score of 42 out of 42, the first Iranian student ever to achieve this. She attended Sharif University of Technology in Tehran. On March 17, 1998, a bus carrying students from Sharif University was involved in a catastrophic accident. 7 of Mirzakhani's classmates were killed. She survived. She went on to earn her PhD from Harvard under Curtis McMullen, himself a Fields medalist, producing a thesis so strong that it yielded papers in each of the 3 most prestigious mathematics journals. Her work was on the topology of Riemann surfaces and their moduli spaces, the abstract mathematical spaces that parameterize all possible shapes a surface can take. She counted geodesics on hyperbolic surfaces. She studied the dynamics of how shapes deform. She mapped the topology of abstraction itself. On August 13, 2014, she became the first woman and first Iranian to win the Fields Medal. She had been diagnosed with breast cancer in 2013. The cancer spread to her liver and bones in 2016. She died on July 14th, 2017, at Stanford Hospital. She was 40 years old. When the Fields Medal was announced in 2014, Iranian state newspapers digitally added a hijab to her photographs. When she died in 2017, for the first time in nearly 40 years since hijab was made compulsory, state-run newspapers published her photo without one. President Rouhani posted her uncovered image on Instagram. Her birthday, May 12th, was declared World Women in Mathematics Day by the International Mathematical Union. She survived a crash that killed 7 friends. She solved problems about the shape of abstract spaces. She became the first woman recognized at the highest level of mathematics. And she died at 40 of the same disease that topology can detect better than statistics. If that does not make you feel something, I do not know what to tell you. So topology governs matter. It governs life. It governs the hidden shape of data and the structure of human vision. Every layer of reality we have examined turns out to be topological underneath. But there is one layer left, the largest one. Space itself, space-time, the fabric of the universe. Einstein proved that space-time has a geometry. General relativity is the most precisely tested theory in the history of physics. Gravitational waves, black holes, the expansion of the universe, all confirmed to extraordinary precision. So surely Einstein's equations tell us the shape of the universe. Surely the most successful physical theory ever constructed can answer the most basic physical question that exists. It cannot. And the reason it cannot is, I think, the most unsettling implication in all of science. Henri Poincaré asked his famous question in 1904 in the 5th supplement to his landmark paper Analysis Citus. The question, in its modern formulation, is this: if a closed three-dimensional manifold has the property that every loop on it can be continuously shrunk to a point, is it necessarily topologically equivalent to a three-sphere? A three-sphere is the three-dimensional analog of the surface of a ball. It is the simplest possible closed three-dimensional space. And Poincaré wanted to know whether being simply connected, having no loops that cannot be contracted, was enough to identify it. This sounds technical. It is technical. But what it really asks is fundamental. It asks whether the local structure of three-dimensional space determines its global shape. Whether knowing what a space looks like at every point, the way general relativity knows what space-time looks like at every point, is enough to tell you the overall topology. The answer, it turned out, is yes. But proving it took 98 years, destroyed careers, and drove the man who finally solved it into permanent seclusion. Let me give you the scoreboard. Stephen Smale proved the conjecture for dimensions 5 and above in 1961 and won the Fields Medal for it. Michael Friedman proved it for dimension 4 in 1982 and also won the Fields Medal. But dimension 3, Poincaré's original dimension, the one that describes the space we actually live in, was the hardest. Every attempt failed. Multiple claimed proofs were retracted. The Clay Mathematics Institute named it one of the 7 Millennium Prize problems in 2000, offering a $1 million prize for its solution. It was considered one of the most important and intractable open problems in all of mathematics. The tool that eventually cracked it was called Ricci flow, and it was invented by Richard Hamilton in 1982. The idea is beautiful. You take a manifold, a curved space, and you let its geometry evolve over time according to an equation that smooths out curvature, like heat diffusion smoothing out temperature differences. High curvature regions flatten, low curvature regions swell. Over time, the geometry flows toward a uniform state. In principle, you could let Ricci flow run on any three manifold, and if it converges to a sphere, you have shown the manifold is a three-sphere. The problem was singularities. Ricci flow can develop points where the curvature blows up to infinity. Think of it like a neck pinching off on a dumbbell-shaped surface. The geometry flows smoothly for a while, and then suddenly, at one point, the curvature shoots to infinity, and the entire process breaks down. Hamilton spent 2 decades developing techniques to handle these singularities. He proved that Ricci flow works perfectly in special cases, like when the curvature is everywhere positive. He showed that the singularities that form are geometrically constrained, that they look like cylinders or round caps at very small scales. But he could not prove the crucial bound, the estimate that would prevent the geometry from collapsing to zero volume at the singularity, which would make the entire argument fall apart. He got tantalizingly close, year after year, paper after paper, always almost there, but never quite closing the gap. It is one of the most sustained near misses in mathematical history. In the mid-1990s, a quiet Russian mathematician named Grigory Perelman wrote Hamilton a letter offering to collaborate on the singularity problem. Hamilton never replied. Perelman decided to work alone for 7 years in near-total isolation at the Steklov Mathematical Institute in St. Petersburg. Perelman worked on Ricci flow, and then, on November 11, 2002, he posted a paper to Archive, not to a journal, to the open access preprint server where anyone can upload a paper without peer review or editorial oversight. He just uploaded it and walked away. The title was The Entropy Formula for the Ricci Flow and its Geometric Applications. He followed it with a second paper on March 10, 2003, and a third on July 17, 2003. The 3 papers, totaling less than 70 pages, contained the solution. The key innovation was something called the no local collapsing theorem, which provided the missing geometric bound that Hamilton needed. Combined with a complete surgery algorithm for handling singularities, Perelman had shown that Ricci flow, properly managed, converges to a geometry that reveals the topological structure of the manifold. The Poincaré conjecture followed as a consequence. So did the much more general Thurston geometrization conjecture, which classifies all compact 3 manifolds. Perelman did not just solve the biggest open problem in topology. He solved something bigger, and the original problem fell out as a corollary. 3 independent teams spent years verifying the proof: Bruce Kleiner and John Lott at the University of Michigan, Huaidong Cao at Lehigh University, and Xiping Zhu at Zhongshan University, John Morgan at Columbia, and Gang Tian at Princeton. All 3 confirmed that the proof was correct. In December 2006, Science magazine named it the breakthrough of the year, the first time a mathematical result had received that honor. And here is where the story becomes something I have trouble telling without getting angry, because what happened next is one of the pettiest episodes in the history of mathematics. In June 2006, Cao and Zhu published a paper in the Asian Journal of Mathematics, edited by Xing-Tung Liao, who is himself a Fields medalist and one of the most prominent mathematicians in the world. The paper's original abstract claimed to give the first written account of a complete proof of the Poincaré conjecture, not a verification of Perelman's proof. A complete proof, as if they had done it themselves. There was an immediate uproar. A page in the Topology paper was found to be essentially identical to content from Klein and Lott's publicly available draft notes. The abstract was revised, but the damage was done. Sylvia Nazar, the author of A Beautiful Mind, and David Gruber wrote a lengthy piece for The New Yorker in August 2006 called Manifold Destiny, which portrayed Yau as seeking undeserved credit for the proof. Yau disputed the characterization. The mathematical community took sides. The politics were ugly. Perelman watched all of this from St. Petersburg, and he made his decision. In August 2006, the International Mathematical Union announced that Perelman had been awarded the Fields Medal, the highest honor in mathematics, given only once every 4 years to mathematicians under the age of 40. The president of the IMU, Sir John Ball, flew to St. Petersburg and spent 10 hours over 2 days trying to persuade Perelman to accept. Perelman declined. He became the first person in the history of the Fields Medal to refuse it. He said, "I am not interested in money or fame. I do not want to be on display like an animal in a zoo." On July 1st, 2010, the Clay Mathematics Institute announced that Perelman had met the conditions for the Millennium Prize, $1 million for proving the Poincaré conjecture. Perelman declined that too. His stated reason was this, and I want to quote it carefully because I think it matters. He said, "The main reason is my disagreement with the organized mathematical community. I do not like their decisions. I consider them unjust." He also said, "I consider that the American mathematician Hamilton's contribution to the solution of the problem is no less than mine." And then he said, the line that I keep turning over in my mind, "It is not people who break ethical standards who are regarded as aliens. It is people like me who are isolated." He resigned from the Steklov Institute in December 2005, before the proof was even formally verified. As of the most recent reports, he lives in seclusion in St. Petersburg with his mother, subsisting on her pension. He has not given an interview since 2006. The Clay Institute used his unclaimed prize money to fund the Poincaré Chair at the Institut Henri Poincaré in Paris, supporting young mathematicians. The man who solved the shape of space pays for young mathematicians to study topology. He just does not do it himself anymore. I want to be careful here because it would be easy to romanticize this as the story of a tortured genius who could not handle the spotlight. I do not think that is what happened. I think Perelman saw something clearly that the rest of the mathematical world refuses to acknowledge. He saw that the system of credit, prizes, and career advancement in mathematics is a game that has nothing to do with the mathematics itself. The mathematics does not care who proved it. The mathematics does not need a prize. And Perelman decided he did not want to participate in a system that pretended otherwise. You can call that eccentric. You can call it, but you cannot call it irrational. He saw the topology of the situation, if you will forgive the metaphor, and concluded that the structure of the reward system was not homeomorphic to the structure of truth. So he left. But his proof does not tell us the shape of the universe, and here is why. General relativity describes the local geometry of space-time. At every point, Einstein's field equations relate the curvature of space-time to the distribution of matter and energy. The equations have been tested to extraordinary precision. Gravitational waves, black holes, the expanding universe, the perihelion of Mercury, gravitational lensing, all confirmed. General relativity is arguably the most successful physical theory ever formulated. But general relativity is local. It tells you what space-time looks like at each point. It does not tell you what the overall shape of space is. Multiple, topologically distinct spaces can have identical local geometry. A flat universe could be infinite Euclidean space, stretching out forever in all directions. Or it could be a 3 torus, a finite space that wraps around itself so that if you travel far enough in one direction, you return to where you started. Both are flat. Both satisfy Einstein's equations, and general relativity cannot distinguish between them. This is the gap. The most successful theory in physics cannot answer the most basic question about the space it describes. Is the universe finite or infinite? Does it wrap around? Is it one piece? These are topological questions. They are the questions that topology was built to answer, and Einstein's equations are silent on all of them. Geoffrey Weeks, a mathematician born on December 10th, 1956, who earned his PhD from Princeton under the legendary William Thurston and won a MacArthur Fellowship in 1999, has spent much of his career working on exactly this problem. His book, The Shape of Space, first published in 1985, is the clearest introduction to cosmic topology that exists. He developed SnapP, a software program for studying hyperbolic 3 manifolds. And he discovered the Weeks manifold, the hyperbolic 3 manifold with the minimum possible volume. In October 2003, Weeks and colleagues including Jean-Pierre Luminet, Alain Riazuelo, Roland Lehoucq, and Jean-Philippe Uzan published a paper in Nature, volume 425, page 593, proposing a specific topology for the universe, the Poincaré dodecahedral space. It is constructed by taking a regular dodecahedron, a 12-faced solid where each face is a regular pentagon, and identifying opposite pentagonal faces after rotating them by 36 degrees. The result is a finite, closed, positively curved 3 manifold with a volume about 120 times smaller than a simply connected 3 sphere of the same curvature. Why would they propose this? Because of data from the Wilkinson Microwave Anisotropy Probe, WMAP. The cosmic microwave background, the afterglow of the Big Bang, has a power spectrum that tells us about the distribution of temperature fluctuations across the sky. At large angular scales, the lowest frequency modes, the quadrupole and octopole, WMAP measured anomalously low power, less variation than the standard infinite universe model predicted, and a small, finite universe naturally explains this. If the universe is finite, it cannot support vibrational modes larger than itself. The low frequency cutoff is a signature of the universe's size. The Poincaré dodecahedral model predicted a cosmic density parameter of approximately 1.013, slightly above 1, consistent with a positively curved universe, just barely larger than the observable horizon. The Planck satellite, which produced more precise measurements in 2013 and 2015, found that the spatial curvature of the universe is very close to flat. The curvature parameter is less than 0.005 in magnitude. No specific compact topology was detected below the diameter of the last scattering surface. But here is the critical point. Compact topologies slightly larger than the observable universe, remain consistent with the data. The Planck results do not rule out a finite universe. They just do not confirm one either. The question is unresolved. We do not know the shape of the universe. The data is ambiguous, and there may be no experiment we can ever perform that would settle the question, because the universe might be finite, but larger than the volume from which light has had time to reach us. The shape of the universe might be unknowable, not because we lack the technology, but because the information is not available. It is beyond our cosmological horizon. The topology of the space we inhabit may be a permanent mystery, not because we are not smart enough, but because the universe is not obligated to show us. And it goes deeper. John Archibald Wheeler proposed in 1955 that at the very smallest scales, at the Planck length of roughly 10 to the minus 35 meters, space-time itself might not be smooth. It might be a roiling, foaming mess of quantum fluctuations, with virtual wormholes and virtual black holes forming and evaporating on timescales of 10 to the minus 43 seconds. Wheeler called this space-time foam. The topology of space at the smallest scales might be wildly, chaotically complex, changing constantly with no fixed shape at all. Recent observations from the Chandra X-ray Observatory, the Fermi Gamma Ray Space Telescope, and the Veritas Telescope Array have found no detectable energy-dependent photon dispersion from distant quasars, which suggests space-time is smooth well below the Planck scale. But the theoretical question remains open. There are also topological defects, cosmic strings, domain walls, magnetic monopoles. Tom Kibble showed in 1976 that these should form during phase transitions in the early universe. As the universe cooled from its initial hot state, different regions of space independently settled into different vacuum states. Where the boundaries of these regions met, topological defects formed, frozen into the fabric of space, like cracks in ice. The monopole problem, the prediction that far too many magnetic monopoles should have been produced, was one of the key motivations for Alan Guth's theory of cosmic inflation in 1981. Inflation would dilute the monopoles to undetectable levels. The Planck data constrained the tension of cosmic strings to gmu over c squared less than 1.5 times 10 to the minus 7th. No cosmological topological defects have been definitively observed, but their theoretical existence means the topology of the early universe was active, dynamic, scarred by phase transitions that shaped the large-scale structure of everything. And then there is string theory, which takes the connection between topology and physical law to its most extreme conclusion. If string theory is correct, there are 10 space-time dimensions, 4 that we observe, 3 of space and 1 of time, and 6 that are hidden, compactified into tiny shapes called Calabi-Yau manifolds at every point in space. These shapes are roughly 10 to the minus 17 centimeters in diameter, far smaller than any particle. The concept traces back to Eugenio Calabi, born in Milan in 1923, who conjectured in 1954 that certain complex manifolds admit Ricci flat metrics, and Xingtong Yao, born in Shantou, China, in 1949, Fields Medal in 1982, who proved the conjecture in 1978. In 1985, Philip Candelas, Gary Horowitz, Andrew Strominger, and Edward Witten showed that compactifying string theory on these Calabi-Yau threefolds preserves the physics we need, published in Nuclear Physics B, volume 258. And here is the part that should keep you awake. The topology of the Calabi-Yau manifold determines the laws of physics. The number of holes, technically the Hodge numbers, determines the number of particle families. The geometry determines coupling constants and particle masses. A Calabi-Yau with 3 specific types of holes yields 3 families of fundamental particles, which is exactly what we observe. The reason there are 3 generations of quarks and leptons, 3 copies of the basic pattern with increasing mass, might be because the invisible 6-dimensional shape curled up at every point in space has 3 holes. But there are an estimated 10 to the 500 possible Calabi-Yau configurations. 10 to the 500. That is a number so large it dwarfs the number of atoms in the observable universe, which is merely around 10 to the 80. Leonard Susskind popularized this idea around 2003 as the string theory landscape. Each configuration gives a different set of physical laws, different particle masses, different force strengths, different constants of nature. String theory says the laws of physics are determined by the topology of hidden dimensions. But it also says there are so many possible topologies that the theory cannot predict which one describes our universe. The laws of physics might be topological accidents. The reason the electron has the mass it has, the reason gravity is as weak as it is, the reason the cosmological constant has the value it has, might not be because of some deep principle. It might be because the 6-dimensional shape at every point in space happens to have this particular topology rather than some other one. There might be no deeper explanation. It might just be a fact about the shape of dimensions we will never see. I want you to feel the full weight of that. You exist because the laws of physics have specific values. The electron mass allows atoms to form. The strength of the electromagnetic force allows chemistry. The cosmological constant allows galaxies to form without the universe ripping itself apart. All of these values might be determined by the number and arrangement of holes in a 6-dimensional shape, smaller than anything we can ever observe. Calabi died in September 2023 at the age of 100, having lived long enough to see his conjecture become the foundation of string theory, but not long enough to know if string theory is correct. Yau, who proved the conjecture, has spent his career trying to find ways to test whether Calabi-Yau compactification describes reality. So far, no definitive test exists. We might be living in a topological accident, and we might never know for certain. And then there is the holographic principle, which takes topology to the very edge of what physics can say about reality. In 1997, Juan Maldacena at the Institute for Advanced Study published a paper, now cited over 20,000 times, proposing that a gravitational theory in the bulk of anti-de Sitter space is exactly equivalent to a quantum field theory living on the boundary, 1 dimension lower. The interior of a volume of space, with all its gravitational dynamics, is completely encoded as a hologram on the lower dimensional boundary. An entire spatial dimension is a projection. This is a statement about topology. It says the relationship between the interior and the boundary of a space is not what you think. The interior is not independent of the boundary. The interior is the boundary, viewed differently. The distinction between inside and on the surface is, once again, not a fundamental feature of reality. Gravity itself might emerge from quantum entanglement patterns on a distant boundary. The solidity of the 3-dimensional space you are sitting in right now might be a topological projection of information encoded on a 2-dimensional surface you will never reach. And the mathematics that describes this is topology. So let me take you back to the question I asked at the beginning of this, because we have been carrying it for 2 hours, and it deserves an honest reckoning. If shape is not real, if the properties we thought defined objects are mathematically optional, then what is real about the physical world? We tried surfaces. Topology showed that inside and outside are optional. We tried matter. Topology showed that the properties of materials are determined by integers in abstract mathematical spaces, not by chemistry. We tried biology. Topology showed that your DNA is knotted and your cells have been performing topology for billions of years. We tried data. Topology found a cancer subtype that statistics could not see. We tried the universe itself. General relativity cannot determine the overall topology of space. The laws of physics might be topological accidents of invisible dimensions, and an entire dimension of space might be a holographic projection. Every layer we examined, every attempt to ground reality in something tangible, something geometric, something local, failed. The answer that kept emerging, whether we were looking at surfaces or quantum materials or DNA or the cosmos, is the same. What is real is what survives when everything else is stripped away. And what survives is not distance, not angle, not size, not curvature, not locality, not even dimensionality. What survives are abstract invariants, integers, equivalence classes, homology groups, properties that describe the structure of reality at a level so fundamental that our language barely has words for them, and our spatial intuition, the neural architecture we evolved to navigate a world of predators and food sources and territorial boundaries, cannot represent them at all. You have spent your entire life navigating by geometry, recognizing objects by shape, judging distances, estimating sizes, and topology says you have been looking at the decoration and ignoring the architecture. The decoration is what changes. The architecture is what stays. And the architecture is abstract. I want to end with the people who discovered this, because their stories have a topology of their own, and it is not a comfortable one. Évariste Galois was born on October 25th, 1811, near Paris. He was a mathematical prodigy of staggering originality. He submitted a paper to the French Academy of Sciences. Augustin Louis Cauchy lost it. His father committed suicide in 1829 after a priest forged malicious epigrams in his name. Galois submitted a second paper. It was in the hands of Joseph Fourier when Fourier died. The paper was never recovered. He submitted a third paper. Simeon Denis Poisson declared it incomprehensible. He was arrested multiple times for his Republican political activities. He was 20 years old and he had revolutionized algebra. But the institutions that should have recognized him had lost his work, let it die with a colleague, and rejected what remained. On the night of May 29th, 1832, Galois stayed up writing. He was preparing for a duel the next morning, probably over a woman named Stéphanie Félicie Poterin du Motel, and he knew he might not survive. He wrote a letter to his friend Auguste Chevalier, summarizing his mathematical ideas, annotating previous manuscripts, adding new theorems in the margins. He wrote, "I have not time, I have not time." Hermann Weyl later called this letter perhaps the most substantial piece of writing in the whole literature of mankind. On the morning of May 30th, he was shot in the abdomen. His opponent and his own seconds left him where he fell. A passing farmer found him. He died the next day at the Hôpital Cochin at 10 in the morning. He refused a priest. His last words, spoken to his brother Alfred, were, "Do not cry, Alfred. I need all my courage to die at 20. He was buried in an unmarked common grave. His papers were published posthumously by Joseph Liouville in 1846, 14 years after his death. They founded group theory, the algebraic machinery that is now foundational to algebraic topology. Every symmetry group, every fundamental group, every homology group in topology traces its intellectual lineage to the scribbled margins of a dying 20-year-old. Georg Cantor was born on March 3, 1845, in St. Petersburg. He studied at Berlin under Weierstrass, Kammer, and Leopold Kronecker. His 1874 paper proving that the real numbers are uncountable, that there are different sizes of infinity, was one of the most important mathematical results of the 19th century. And Leopold Kronecker, his former teacher and the gatekeeper of the Berlin mathematical establishment, spent decades trying to destroy him. Kronecker called Cantor a scientific charlatan, a renegade, and a corrupter of youth. He tried to block publications. He campaigned against Cantor's appointment to positions he deserved. His dictum, "God made the integers, all else is the work of man," was a direct assault on Cantor's transfinite numbers. Cantor's first mental breakdown came in the summer of 1884. He was 39. He was diagnosed with cyclic manic depression. Over the following decades, he was hospitalized repeatedly. In December 1899, his youngest son, Rudolf, died suddenly. After that, the breakdowns became more frequent. He took medical leave from the University of Halle in 1902, 1904, and 1907. During episodes, he developed bizarre fixations, publishing pamphlets claiming Francis Bacon wrote Shakespeare's plays. In June 1917, he entered a psychiatric clinic in Halle. He continually wrote to his wife, begging to come home. He was never released. He died on January 6, 1918, of a heart attack, malnourished during wartime, in the sanatorium. He was 72. David Hilbert called Cantor's work the finest product of mathematical genius and one of the supreme achievements of purely intellectual human activity. The continuum hypothesis that Cantor formulated and that tormented him was later proved to be literally undecidable within standard set theory by Kurt Gödel in 1938 and Paul Cohen in 1963. The question that consumed him and arguably destroyed his mental health cannot be answered, not because it is too hard, because it has no answer within the axiomatic system that mathematics uses. The system itself is incomplete, and Cantor's set theory, the theory that Kronecker despised, is the very foundation on which topological spaces are defined. Every topological space is at bottom a set with a structure. Cantor built the foundation. It cost him everything. And then there is Vaughan Jones, born December 31st, 1952. Discovered the Jones polynomial by accident in 1984, connecting operator algebras to knot theory in a way that nobody had imagined possible. Won the Fields Medal in 1990, wore an all-blacks jersey to the ceremony. His work bridged 5 different branches of mathematics and physics. Joan Berman described her astonishment when she saw what he had found. Alain Connes called his polynomial one of the great jewels of the unity of mathematics. The Jones polynomial now underpins topological quantum computing, a technology that Microsoft is spending billions of dollars to develop, a technology that could transform civilization. Vaughan Jones died on September 6, 2020, at age 67, from complications of a severe ear infection. A man whose abstract mathematical work may power the next century of computing died from something a course of antibiotics should have handled. There is a topology to that, a shape to the contrast between the permanence of his ideas and the fragility of his life that I do not think anyone could invent. It is too precise, too cruel, too perfectly structured to be anything other than real. Emmy Noether, denied a salary until she was 41, fired by the Nazis, dead at 53. Her theorem is carved into the foundation of modern physics. Every conservation law in the Standard Model is a consequence of her work, and she spent 16 years working for free. Maryam Mirzakhani survived a bus crash that killed 7 friends, won the Fields Medal, died of cancer at 40. The newspapers that censored her image in life published her uncovered face in death. She mapped the topology of surfaces that exist only in mathematical abstraction, and the topology of her own life, the survivals and the losses, has a shape that no one would design and no one can forget. And Grigory Perelman, alive as far as anyone knows in a small apartment in St. Petersburg with his mother. He solved the Poincaré conjecture. He solved the Thurston geometrization conjecture. He classified the topology of 3-dimensional space, and then he concluded that the mathematical community's system of prizes and credit was topologically equivalent to something he wanted no part of. The structure of the reward system could be continuously deformed into pettiness. So he left. He took his understanding of the shape of space and he went home. I think Perelman saw something that the rest of us are only now beginning to reckon with. Topology tells you that the real properties of things are not the ones you can see. The real properties are the invariants, the things that survive when everything visible is stripped away. And if you apply that principle to human institutions, to the systems of credit and fame and money that govern how knowledge is produced and rewarded, what you find is that the visible properties, the prizes, the publications, the positions, can be continuously deformed without changing the underlying topology, which is the mathematics itself. The mathematics does not need the institutions need the mathematics. And Perelman decided he did not need the institutions either. The mathematics survives. That is the topological invariant of human knowledge. The people who discover it are stretched, compressed, broken, and forgotten. Galois died at 20. Cantor died in a sanatorium. Noether died in exile. Mirzakhani died at 40. Jones died from an ear infection. And the mathematics does not change. It cannot be deformed. It cannot be torn. It cannot be made to forget what it knows. It simply is. You came here because the title told you that shape was never real. And it was not. The properties you thought defined the world, the angles, the distances, the sizes, the familiar geometry of everyday objects, are the properties that topology discards. What remains are integers, invariants, equivalence classes, abstract structures living in mathematical spaces that you will never see and can never visualize. These are the real properties, the ones that determine whether matter conducts, whether DNA survives, whether data conceals a hidden structure, whether the universe wraps around itself. You now know this. You cannot unknow it. The coffee mug in your hand has a genus of 1, same as the donut in the bakery window. The material of your phone screen has a Chern number that determines whether electrons flow. Your DNA was unknotted by a topoisomerase minutes ago. The space you are sitting in has a topology that Einstein's equations cannot determine. And the 6 hidden dimensions of string theory, if they exist, have a shape that set the electron mass, the strength of gravity, and every other constant of nature. And there are 10 to the 500 other shapes that would have given different constants, different forces, a different universe entirely. And nobody talks about this. The 2016 Nobel Prize was given for work done in the 70s and 80s. The breast cancer result from 2011 changed nothing about clinical practice. Perelman's proof was nearly stolen. Noether worked without pay. The field that governs the deepest structure of reality spent its first century without even a consistent name. The universe has a shape, but shape was never real. What is real is the topology, and the topology is something you can describe, something you can prove theorems about, something you can use to find cancers and build quantum computers and classify the very fabric of space. But it is not something you can hold in your hand. It is not something your eyes were built to see. It is the structure underneath everything, and it does not look like anything at all. It just is, and now you know.